Let's talk about fractional distillation. Why? Because it rules our lives. Folks. Oh, yes it does. 60% of the stuff we use comes from petroleum. Don't know if it's 60%. That's one of those statistics that I made up just on the fly. But it's a lot of stuff. A lot of stuff. Where does petroleum come from? Crude oil. Dirty oil. What is crude oil? Crude oil is a heterogeneous mixture of various types of hydrocarbons. So when it comes from the ground, it's absolutely useless to us. We have to separate it out into all the different forms that we use. We separate it out using their one weakness that they have: boiling points. Everyone has their own boiling point. Think of it as their own breaking point, their weakness. How do you get to somebody? By exploiting their weaknesses, right? How do you separate two people? Exploiting their weaknesses. Well, the weakness of all substances is their boiling point. Once they hit their boiling point, they have to become gas. It doesn't matter if no one joins them around them. They have to become gas. So the way that they separate crude oil into all the many different types of useful hydrocarbons is by using their boiling points against them. Teeny tiny little molecules are going to have low boiling points. So they're going to scurry on out first. Then the larger, heavier molecules, which are more liquid-like, will have to be made into a gas at a much higher temperature. And then it gets separated out using this technique. Cool video. Watch. I love English accents.
In this video, you will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics. However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas. They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required, a higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule. Let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapour form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still high, some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column. The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapour, and eventually the vapours get too cool, condense, and are collected as liquids in the trays. Small molecules have low boiling points, and so condense much higher in the column, where the temperature is cooler still. As you can see, Hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars,
What we call gasoline.
naphtha, used in the manufacture of chemicals, kerosene as aircraft fuel, diesel oil, used as fuels for vans, cars and lorries, and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling points. You should understand that small chain molecules are collected at the top of the column since they have lower boiling points, and larger chain molecules are collected further down the column as these have higher boiling points.
So it's very key to us using these resources, folks. These things, and by the way, the people who work in these areas right here, they're the ones who are on strike now. This is what goes on in Texas. You know, when they talk about oil refineries, this is it. This is it. It's a process of separating crude oil that comes from a ship or a pipeline into all the various forms that we use. If you've ever gone from, has anyone ever traveled from Texas to back home, and you've seen whole fields? Have you seen that? It's just as far as the eye can see.
My grandpa lives in biogas, so that's all you see.
There's Texas City is a whole city made up of these things, and you're right. That's all you see. These columns. Now you know what these columns are used for. What are the first hydrocarbons to separate, and what are the characteristics? What are they? The small ones, okay, and they tend to be gassy. Those of you, I mean, we're all human beings. We all emit some of these gases every morning, sometimes throughout the day, okay, and that's natural gas. That's stuff that we produce, cows produce, the earth produces. The second hydrocarbons to separate are airplane and automobile fuels. They have a little bit of attraction, so they tend to be liquids. And finally, the big heavy ones are the ones that we use in many cases for plastics. We also use them for tar, for roads and stuff like that, making rubber. So, when we talk about this type of chemistry, we talk about organic chemistry. It is the study of hydrocarbons and their derivatives. The study of hydrocarbons and their derivatives. They are called organic because early chemists felt or believed that these chemicals only came from living material, thus organic. Now we know it's not true, but the name has stuck. Organic. What is a carbon chain? A carbon chain is basically the fact that carbons tend to link together to form chains of molecules. I like to think of carbon as a 2x2. Lego. You know what I'm talking about? You can build the world with a 2x2, correct? It'll take you a long time, but you can build anything you want with a 2x2. Consider carbon as a 2x2 brick of Legos. Okay? The smallest chain possible. And then we actually have 4x4s and 2x4s and 6x6s, no, 6x2s and stuff like that. So Legos come in various forms. In the same way, organic molecules come in various types of chains. Why is this ability to form chains so important? Because the fact is 99.5% of all the molecules known to man are these types of molecules, organic molecules. We here in chemistry, we've only studied 0.5% of all the chemicals known to man. Why do we study the minority? Because organic chemistry is a different ball game. We're going to cover organic chemistry to a small extent, much greater than the honors classes and much greater than the other chemistry classes, because I truly believe that organic chemistry is very important to our lives, and I want you to have a basic understanding. Okay, but organic chemistry is a completely different ball game. You'll see what I mean. What holds these carbon atoms together? Covalent bonds. Covalent bonds. Who can, once again, tell me the difference between a covalent bond and an ionic bond? Jeffrey. Okay, that tells me what they're between, but it doesn't tell me what happens. What does a metal and a non-metal do? Okay, so there is a transfer of electrons in an ionic bond, and in a covalent bond there is sharing. Sharing. So covalent bonds involve sharing of electrons. Ionic bonds involve a transfer of electrons. Sharing for covalent, transfer for ionic. And that's review. And Jeff was absolutely correct for number 13. Ionic is between a metal and a non-metal. Covalent is between a non-metal, non-metal. Ionic is between a metal and a non-metal, and covalent is between a non-metal, non-metal. Okay, so we've learned how to write chemical formulas, and most of you guys are pretty good at it. Good job. But sometimes chemical formulas are not good enough to help us explain how a molecule is going to work. We actually have to see what they look like. So, dot diagrams are going to help us understand how molecular compounds, primarily, how they work and what they look like. They'll help us today. They'll help us understand why ionic bonds are what they are. But tomorrow we're going to deal with molecular compounds. It's going to be kind of fun. What are Lewis dot diagrams? It was named after this American scientist. So rare that I say that, American scientist. But he was, Gilbert Newton Lewis. And what he did is he came up with a way of symbolizing the number of outer shell electrons that are around the nucleus of most elements. So you use dots to represent those outermost electrons. Lewis dot diagrams is the symbol of the element and the dots drawn around it to represent the outermost electrons. The symbol of the elements and the dots drawn around it in order to represent the outermost electrons. All right, I'm going to need 11 of you guys to help me out here. Let's start with hydrogen. What is the electron configuration for hydrogen? Raise your hand. Jeff gets to do the easiest one. That means everyone else has to do the harder ones. Yes, Jeff? 1s1. So what does that mean? That means we have one outer shell electron. So what does that mean? That means that the dot diagram, you draw it and you put a dot right beside it. Okay, what we're going to do is we're going to represent the 8 electrons that can exist in the outer shell by placing dots around them. So we have 1 s orbital and 3 p orbitals for a total of 8 electrons. So that's what we're going to do. They're going to have any number between 1 and 8. So if you're in an accident and you lose 2 fingers, you can still do this. You can still do this. If you lose 3 fingers, then you're going to be handicapped. Okay? But you have 2 fingers to spare if you decide to become a chemist, because all we deal with are really numbers between 1 and 8. All right? Helium. Who can do the electron configuration for helium? Thank you, Riker.
1s2.
1s2. So how many outer shell electrons does it have?
2.
So where are we going to place these 2 dots?
On the right.
Excellent. Okay? I'm going to start lithium up here for a reason. You will see why. What is lithium's condensed electron configuration?
8.
Randy? HE's insides. So we don't care about those 2 electrons. Those are inside. And beyond it? Beyond it?
I don't know.
Okay, let's look back here on the periodic table. So it's HE, and then right here is 2s1.
Yeah.
2s1. Why did I place it right next to hydrogen? How many outer shell electrons does it have?
1.
1. So just like hydrogen, it only has 1 dot. Jackson, we're going to put beryllium right next to helium. Let's see why. What's beryllium's insides look like? What noble gas is inside of it? Very good. And what's beyond helium? 2s2. So just like helium, beryllium should look like what, Jackson? All right, now we go to uncharted territory. Spencer, boron has what insides? What noble gas is inside of it? Spence, look back here. So there's beryllium. What noble gas is inside? Neon? Neon is beyond it, my friend. What noble gas is up
Helium.
and over? Helium. All right, let's continue from there. So, Spencer, boron has these 2. What do we call these 2? 2s2, and it has this one. Okay, a little dyslexia there. 2p1. Okay, very good, Spencer. So, boron will look like what? Well, how many outer shell electrons does it have? Take out your 8 fingers. 3. It's in the 3rd column, so 3. So, how many dots go on the right? Just like these. This is 2. This is going to be 2. And then the 3rd one goes. Does it matter where?
No.
No. So let's put it on top, Spence. That is boron. That is boron. Spence, you kind of struggled with that one, but I am confident that you see the pattern now. So let's do carbon. Yeah. Yes. 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 So it's going to be, look like what? Yes. Now be careful. Okay, hold on. Before you answer this, remember back when we were doing the RA game, and I told you you could only place 1 student per room until you have no other choice. There was a reason for that. I called it Hund's rule. Hund's rule. Okay? Which states you can only place an electron 1 at a time. When you have multiple orbitals, like P's have 3, you can only place them 1 at a time until you have no other choice but to go back and double them up. So what will it look like with Hund's rule? Yes, absolutely correct. Good job, Spencer. Bailey, nitrogen, pick up the pattern. So nitrogen is going to look like careful, how many rooms do you have? This one, and this one. And how many more students do you have? Well, we've placed these right here. Now we have 3 more to go. Yes. Good job. Oxygen. Ben. Follow the pattern. Yes. 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 So oxygen is going to look like. Yes. 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 Very good. Good job. Hunter, follow the pattern.
HE, 2S2, 2P5. We got 2 on the right, and 1 on the top, and right there, 1 on the bottom, another on the top, and another on the bottom.
Very good. M and E, neon. Any. So, does neon have any bonding places? No. So neon is not going to bond with anything. How many bonding places does fluorine have?
1.
Oxygen,
2.
nitrogen,
3.
and we're going to see tomorrow why that becomes so important. All right, 1 more to go. Asher, Chance, sodium. Why am I going to start way up here again? What? The pattern is going to repeat itself. Nope. I said 11 elements. The first 11 elements, and that's your 11th one. So, what will magnesium be? Jackson? Not Jackson. Bailey, what will magnesium look like? Follow the pattern. Kelsey, what will aluminum look like? How do you know? Follow the pattern. Silicon. Isaac. How do you know? Follow the pattern. Phosphorus. Serenity. Follow the pattern. Those are atoms. How do we represent ions? By using brackets and a charge. Positive ions are going to be the metals. They will have 1, in which case they'll need 7, or they'll have 2, in which case they'll need 6, or they'll have 3, in which case they'll need 5. Folks, these things will always follow the path of least resistance. So metals would rather lose electrons and be like the noble gas inside of it than gain electrons. Nonmetals will want to gain electrons, so they will have dots. I like to think of them, positive ions, as being naked, which is what we call being in the South and not having any clothes on. That woman's naked, right? Go to Myrtle Beach, that woman's naked, Myrtle. All right, so naked means no dots, and then negative ions will be full. Negative ions will be full. These are easy, but I'm going to show you the reason behind what we do, and then I'll show you how easy you can just do it by yourself. NaCl. Let's see. Who have I not called on? Jackson. Let's see. Gracie. Na. Look at where it's at on the periodic table. How many dots? Very good. Cl. Devon. Look on the periodic table. Tell me how many dots. You only have to count to 8, bud. 7. 8, 7. 87. Okay. Devon, is this guy happy? Chlorine. What does it need? So let's put a frowny face on it. Gracie, is yours happy? Why? Okay, so when they come together, Gracie, you have 1 dot. Devon, you have 7. Do you guys want to talk about it? No? Anything you want, Devon? He wants a dot. Gracie, what do you think? So there is a transfer. So now sodium has lost its electron. We say sodium is naked. No, naked is not right. Naked is just somebody that's lost their clothes. And chlorine is completely full. Do you need the brackets? Yes. Do you need the dots? Yes. Do you need the charges? Yes. What if I forget, Mr. Moreno? It's wrong.
The whole thing? Or just half?
The whole thing. The positive ions are naked with brackets and a plus. The negative ions are full with brackets and a negative. And you have to tell me how many negatives. The brackets tell you that they have gained or lost. So it's an unnatural situation. All right, who would like to do, everyone's had a chance to go, so who would like to do CAF2? Go, Jackson. Go, Jackson. Go, 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 Jackson. What?
CA has 2 dots.
All right.
And then
Fluorine.
it has 7.
Yes. If in doubt, take out your fingers and count. You'll count to 7. All right, so if you were fluorine, what would you ask calcium?
You would ask him for 1 dot.
But Emmy, you're calcium, so you would say, no, you want to get rid of your dots, but what's your problem? You have 2. So what are you going to ask Jackson?
Make another one for him.
No. Ask him if he's got a brother that looks just like him. Ask him.
Looks just like you.
Ah, so here comes the brother. There is Maxon. Jackson and Maxon. Okay, so Emmy, what are you going to ask Maxon? Give him your dot. And Maxon goes, yay, I've got a dot now. I'm just like Jackson. So, one big happy family, folks.
You have to put
There's
the brackets-
Emmy. She lost her dots. And now she's positive 2. Here is Jackson and here is Maxon. They've gained dots from Emmy, and now they're negative.
You have to put the bracket on both.
Yes, it has to look like this. It would be wrong. You got to put the dots. The dots have to be around the negative ions, and it has to be empty. It has to be naked. That is what I'm expecting. Anything other than that is wrong. All right, Ben, you and Kelsey are going to play now. You want to be aluminum or oxygen? You're the senior. I'm going to give you a choice. Aluminum. How many dots do you have? Aluminum? Just got to count to 8, son. This isn't hard.
Technically, it's not aluminum, it's
Aluminium. All right, Kelsey, you're oxygen. How many dots do you have? What do you want, Kelsey? What do you want out of life?
A kid.
2 more dots?
You want a kid
What do you want? Aluminium?
A couple dots.
No, you would need 5, son.
Oh.
Not a couple. Couple's not going to help you. So you're so far away that it'd be best if you did what? Gave them away. Hey, you got 3. She needs 2. You guys want to, get together and transfer some electrons? All right. So Kelsey, how much do you want from him? No, you 2. And do you want to give her 2? Yeah, of course. That's what metals do. They give electrons. Okay, so now that makes her into a negative ion. And are you happy, aluminium?
Yes.
No, you're not.
No.
Now you're desperate, because how close are you to becoming like a noble gas?
Very close.
Very close. So now you're even more desperate than you were. So what are you going to ask her?
Do you want this one?
No, she doesn't want it. She's full.
You have a sister.
Oh, yes, she does. Hey, Kelsey, go get Melcy. Here's Melcy. Hey, how you doing? Ooh, Ben, you're such a stud. Good to see you, aluminum. You got something for me? Yeah, you got something for me? So, Ben, what do you do?
Yeah, I got something for you.
All right, so now, Ben, you are completely ionized. You've lost your 3 electrons. You're happy now. Is Melcy happy?
No.
So what does Melcy ask? You can play the part of Melcy, Bailey. So you're Melcy. So what do you ask? For what? Do you have a brother?
Yeah.
What's his name?
Ren.
Ren and Ben. So Ren comes around, and he's got 3 electrons. So what happens now? Can Ren have another dot? Devon, you can be Ren.
Why not?
Why not?
Take it. Take it. Take it away.
So now Bailey's happy. Okay? So, Devon, you're Ren. Are you happy? Nope. So what do you want? What?
Triplet.
You want a triplet. So what's your sister's name? Your other sister's name, Kelsey? Felcy. Felcy. Kelsey, Felcy, and Melcy. All right. Ren, what are you going to ask? What's her name again?
Kelsey.
Felcy. What are you going to ask Felcy to do?
Take my dot.
And girls say that you're not romantic. Oh my gosh.
Take my dots.
This is it. We ought to have Dippin' Dots. Just take out the Dippin' Dots and we can all play with little Dippin' Dots and eat them.
That'd be
And-
kind of messy.
yeah, I would. They'll melt. That monstrosity is the dot diagram for aluminum oxide.
That's a lie.
All right, let me show you how to do it easily without imagining you're these things, right? Okay, how many Ks do we have?
2.
Is K a metal or non-metal? Metal. So they're naked. What's the charge on K? +1. How many oxygens do you have? Metal or non-metal? So fill them up. Brackets, charge, done. No, the first three I tried to show you why they do what they do. But this is just, let's just do it. Now that we know how to do it, let's just do it. And that, yes.
I use the bathroom.
Can you?
May I?
Yes, you may.
That's what I say.
All right, so you've now learned how to do dot diagrams for individual elements, and then what if they get involved in an ionic situation. You now know how to do that as well. Tomorrow, we'll learn how to do covalent molecules.